530.
All right, what is, you're gonna have to give me the specs on that.
10 megahertz magnetic field cycles in a fluid,
Okay, go ahead.
in a fluid for which the propagation velocity is 1 times 10 to the 8 milliseconds.
Meters per second.
Yes, sir.
Go ahead.
Initially, we had H00 equals 2AX.
Amps per meter.
Yes, sir. And the amplitude drops 1 amp per meter after the wave travels 5 meters in a y direction.
So it at 5 meters, it goes down to what value?
It drops 1 amp per meter.
All right, so if it's dropping one amp per meter, you're talking, it's a per meter, like per meter? In other words, if it's dropping, if that its value to 1 amp per meter every meter, that would be an amp per meter. Then if this is 5 meters, this would be going down. I think,
You might want to read it. I'm a little confused.
gosh, my glasses.
It says the amplitude drops 1 amp per meter after the wave travels 5
All right,
meters.
now that's different. It says it goes down to a value of 1 amp, 1 AX amp per meter. It was at 2 and it drops at 5 meters. That's what it's actually saying. All right, go ahead.
Find the general expression for this wave and find the instantaneous expression for
The
the
H
E field.
The E field? Okay.
Yes, sir.
All right, well, for this one, we have to remember that in general, if we talk about H, it has a magnitude H0. This is for a plane wave. And then it's gonna have e to the minus alpha z times e to the minus j beta z in the AX direction. This is for a forward propagating, a wave propagating in the Z direction. All right, now, what he's talking about here, and what you can obtain from this, is if you take a look at, he's given us a velocity of propagation and a frequency. Well, first, I know phase velocity right here is equal to omega over beta. Do y'all follow me on this? That's true in any media. Well, omega is 2 pi f, so it's 2 pi times f, which is 10 megahertz, that's 10 to the 7th hertz, divided by beta is equal to the phase velocity, which is 1 times 10 to the 8th, or 10 to the 8th. That means I can get beta right away. I can say beta is equal to 2 pi times 10 to the 7th divided by 10 to the 8th, and that's 2 pi times 10 to the minus 1. And that's radians per meter. So I've got beta. Now to get alpha, when I look here, I can take the magnitude, let me do it this way. This is in the phasor domain. Do you all agree with that? If we want it in the time domain, H would be equal to H0 e to the minus alpha z, and then it would be cosine of omega t minus beta z. And there could be possibly a phase angle, but he doesn't give us enough information to obtain any phase angle, so you just assume it's 0. And this would be in the AX direction. Now, if you look at this, or this one, and if you take the magnitude of H, better yet, let's use this one, then it becomes simply H0 e to the minus alpha z would be, in the AX direction, would be the magnitude of H anywhere. Now we can get alpha because we know how much it decays in 5 meters. Do y'all follow me, class? I want to make sure you do. Got this? All right. We get beta from this. We're going to get alpha from this. So now when we take a look at this, we can say that since this is the equation I'm using, 5 meters away, it's 1 amp per meter. So it's 1 AX here is equal to 2 AX here. And then it's e to the minus alpha times 5, because it's 5 meters. Y'all agree with me? And now, if we take, and just go ahead and calculate it, I have 1/2 is equal to e to the minus alpha times 5, or the natural log of 1/2 is equal to minus alpha times 5, or alpha is equal to minus the natural log of 1/2 divided by 5, and you can give me that, anyone. I'm sure he did it this way, but
0.138.
0.138, and that's Napiers per meter. So now we have alpha and beta, right? And the next thing we need is, let's see. We have gamma equal to alpha plus j beta, and when we get the ratio of E to H, magnitude, that's eta, right? And eta is equal to it's equal to the square root of j omega mu over sigma plus j omega epsilon. And if I take that, and I know that gamma is equal to the square root of j omega mu times sigma plus j omega epsilon as such, now I can go ahead, since I have, let's see, the easy way would be, what I need is eta right here. That's what I need to get my value of E. So if I take this into consideration, I can say that the square root of j, let me see here, this is going to be equal to this is equal to gamma times j omega mu, I believe. Yeah. Let's see. Yeah, that would be the case, right? And if that's the case, now we can get eta because we have eta would be equal to j times 2 pi times 10 to the 7th times mu naught. Does it say non-magnetic in there? Anywhere? You're gonna have to make this assumption, because if there's a mu relative that's not equal to 1, then this won't work, and this is about the only way I can see getting at the answer. That's gonna be the case, and then you have over the propagation, which is alpha 0.138 plus j, and beta was 2 pi times 10 to the minus 1. And that should be eta. Can you give me eta, anyone? Does the book do it this way in the solutions or not? Anybody look? You must have. Remember?
I don't think it was quite right there.
That's all right. Did anybody look at the solution for this one? Because this is a good problem. It forces you to think beyond the usual way of doing business. This is the one thing you gotta catch on this one. Right there.
I don't see eta on here.
No, you're gonna have to have it, I think. Well, there might be enough.
It doesn't say it's non-magnetic though. I did check.
Well, I think it's an assumption. What'd you get?
119.8 plus 26.3
Could you give me a magnitude and a phase? But really, magnitude's all I need.
Okay.
Use the book solution.
He uses K instead of beta. Okay. Go ahead, tell me.
122.7.
122.7 at an angle of
12.4.
degrees, right?
Yes.
All right, now, since we have H here, we can get the E field too. Now our E field, if we assume, by the way, that it has a phase of 0 here, remember H naught is just going to be equal to the 2. We've got alpha, or we've got beta, so this equation is solved, basically. We have all the unknowns. Now for the E field, I can say the E field is equal to magnitude of H naught, I'll put this down first, divided by magnitude of eta, then it's going to be times eta, divided by, times magnitude of eta, and then it's going to be e to the minus alpha z, and it's going to be a cosine of omega t minus beta z, and then the phase angle here, I'll show you how I'm getting this. Remember that I said that there were two things that made life easy. One is knowing that h is equal to 1 over eta, a rho, that's the unit vector in the direction of propagation, crossed into the E field. And the E was equal to minus eta, a rho, crossed into the H field. Well, if you take a look at this right here, we're going to have minus the magnitude of eta times the magnitude, well really, then the phase angle is going to, for this one right here, let me do it from there, and I don't want to confuse you on this one. I'm going to try to give myself just a little more room right here. Since we have H is equal to 1 over eta, a rho, crossed into E here, I know if I take this and I do this, this would be equal to 1 over magnitude of eta, a rho, crossed into the E field, but then there would be e to the minus j phase of eta up here. And therefore the H field here in the time domain would be equal to the magnitude of the E field, or really E naught, magnitude of the E field divided by magnitude of eta times cosine of omega t, and then it's going to be minus beta z minus the phase angle. Now for the E field is minus eta, a rho, crossed into H, and that means this becomes minus magnitude of eta, and then it's going to be times magnitude of H right here, and it'll be cosine of omega t minus beta z, and it's going to be plus the phase angle, plus e to the j phase angle of eta right there. But that minus sign can be gotten rid of, and you can bring in here and add 180 degrees to this. Either add or subtract 180 degrees or pi. If you're in radians, it would be plus or minus pi. Are you with me on that? That's how you get rid of a minus sign in front of a cosine. Just add 180 degrees to it. So for this one, that means we have eta of 122.7. Then we have an H field of 2. Then we have cosine of the omega t. Omega is just 2 pi times f minus beta, and we've got beta z. And then I'm going to go ahead and put the phase angle, it would actually be just phase angle, not an e to that, just phase angle of theta n. It's going to be plus the phase angle of 12.4. And you can subtract 180 degrees, but this really should be in radians. I'm leaving it in degrees. So what do you get for the E field? So that's 245.4, is that right? Times cosine of omega t minus beta z plus, and that should be in radians, whatever. Does he have that? The magnitude of E? Can you see it? Tell you what, check this first. Does he have this for beta? Beta would be 2 pi is what, 6 point something? Can anybody give that to me? Pi is 3.14, 2 times is 6 point, about 6 point. So this is about 0.63, 0.63 rads per meter. Does he have that for
Yeah.
beta?
He's got that right.
All right, now does he have this for alpha? Oh, where is alpha? Did I erase it? No, alpha 0.138?
I don't see that.
You'll have to.
Yeah, that was right.
He's got alpha, all right. So if we have alpha and beta right, then necessarily we have this right too. Do you see what I'm saying? Because it has, if alpha and beta are right, then we know that gamma divided into j omega mu has to be equal to eta, right? Are you with me on this? The way I got this, by the way, is if you think what gamma is, it's j omega mu times sigma plus j omega epsilon. You stick that in here, and you have j omega mu to the first power divided by j omega u to the 1/2, which means it would be j omega u to the, or mu to the 1/2 divided by sigma plus j omega epsilon. It would be this. So that means we have this right? Now, once we have that right, we have the magnitude of E for sure, right? And the only question is the phase. Well, he was unspecific about where the phase is 0 for the H field, so you can't be specific where the phase is for the E field, except to say one thing. You know the phase will have a separation of the 100 or the 12.4 degrees minus or plus 180 degrees. You'll know that's the phase difference between the two, but you don't know the actual absolute phase because it's not specified. And that's assuming it's non-magnetic. Out of curiosity, does he have 245.4 volts per meter for the E field?
Yeah, it's 400 pi divided by 5.
Well, just check that, would you? 400 pi divided by 5. I hate you.
251.
All right, 251. Where did we get a round off there?
Technically, the alpha was 0.1386. That's not gonna do it, is it?
I don't know. 0.1386. It may, because you were at 251 versus 245. That's super small. That could do it right there. But it's somewhere in the rounding off. All right. And he just gives you the magnitude that you feel. Oh, I wish I had my glasses. Oh gosh. Yeah, he has the minus 2 pi over 3 thing there. So he does. Can you go up a little? Go. Keep going. All right, now see, he gives a phase for that H field. That's the problem. Oh, wait a second. There's no alpha in that one. See, there's no e to the minus alpha z. There's something goofy about that solution. Is this out of Wentworth, or?
Mm-hmm. Yeah, that's what I was talking about. I didn't see it.
No, that's wrong. There has to be an alpha term in there because he's saying it's decaying by a certain rate. So his h in there is wrong. There should be e to the minus alpha z in front of that thing, if you look on his solutions.
Yeah, this is his book.
Yeah, but that h field's wrong. Anytime that you have decay in one, you have decay in E and H. So that's wrong. But this is how you would get the relative magnitudes of the E field, right? And obviously an equation for the H field. The real problem is right here. You don't know what the phase angle was to start with. He has 2 pi over 3s in his starting phase, which I don't know how he got that, but forget that for now. Don't worry about that. Mainly these problems, you don't worry about the time domain waveform. Almost always what you do is you want to know the magnitude of both the E and the H field, the decay constant alpha, beta. Those are the things you want to know. And that's the essential. Okay. Any other problems? That's it. You know, the thing about this problem that's really good is you're used to having sigma, mu, epsilon given, and the frequency, then you calculate eta and you calculate gamma, right? Here, it's not specified. He gives you like an observation, and you have to derive what beta or what alpha is, and then what beta is too, instead of derive it from some graphical information or measurements. I want to say one more thing about this problem before I'm done. when we had, I'm gonna start with H. When we had H is equal to 1 over eta times A rho crossed into the E field. From here, remember, that's a phasor, right? This is phasor domain quantities. This is not time domain. Now, what we think of is we have 1 over eta. Eta is really magnitude of eta, and it's at a phase, e to the j phase of eta here, A rho crossed into the E field. That also means we have 1 over the magnitude of eta, right? And then when this phase comes on top, it becomes e to the minus j phase angle theta n, A rho crossed into the E field, right? And that's still H. Now if we want in the time domain form, H becomes the real part of e to the j omega t, right there, times H phasor. And that would be times e to the minus j phase angle of theta n over the magnitude of eta. And what I can do is take the E field phasor and just leave it in here, and then take the product of A rho crossed into a unit vector in the direction of the E field. See, I can take the vector sense of the E field and take it outside that real part. Are you with me? So this gives me the direction of propagation, or excuse me, the orientation of the H field, all right, dependent on the E field's orientation. But the actual information about the signature, the time varying signature and the decay is right in here. Now the E field in general, you have to have an equation for it to get the H field. But for the E field, if you look at this, normally the E field would be something like, it would be saying the AX direction, and it would be e to the minus alpha z, e to the minus j beta z, and there may be a phase angle here, but for now, if there was e to the, say, j theta right here, well, when I put that in here, and I'll do it, just do the whole thing for you. Now, if I put the H field in here, I get the real part of 1 over the magnitude of eta, and then I get, let me put an E naught here, I didn't do that. You're gonna get E naught right here, then it's gonna be e to the minus alpha z, e to the minus j beta z, and then it's gonna be quantity beta z plus the phase angle, the actual phase angle of eta, and then you can add any other phase to it. E to the j theta sub e, and then it's A rho crossed into AE, pardon me. And that means H would be equal to E naught over the magnitude of eta right here, e to the minus alpha z, and then, because this, when I take this times e to the j omega t, I'm sorry, I forgot to put that in there, put that e to the j omega t, this gets added to that, and you have e to the j quantity omega t minus beta z minus the phase angle of n. So you have a cosine waveform that will come out omega t minus beta z minus the phase angle associated with n, and then plus the initial phase on E, and it would be in a direction A rho crossed into AE. Now let me just mention a few things so you got this. I know you're a little probably unfamiliar with this process. This just gets the vector sense of it, all right? That's the only thing, if you have an E field that's in a phasor form, now you get the vector sense for the H field here. The eta here, the thing about it is, it has a magnitude and a phase angle. When the phase angle comes up top, it changes polarity. Whatever it is, if it's a plus, if it's 30 degrees downstairs, it's minus 30 degrees when it's in the numerator. Then you have to add, you have to multiply by j omega t times this times the E field. Well, the E field's expression is this. The phase is here and here. So all these e to the j, like an omega t minus beta z minus the phase angle of the complex, the phase angle of the intrinsic impedance, plus the original phase angle, all those things have to be put into this equation right here. Follow me on that? Now, one of the things you get, let's assume there is no initial phase right here on that E field. Let's get rid of that phase. So assume it's zero. Then the phase difference between E and H, if you're looking at E field having the zero phase, follow me on that? It's got no phase shift. Then the H field will always be lagging behind it by the phase angle associated with eta. So if it's 122 degrees at an angle of 122 point whatever that was, at an angle of 12 degrees, this would be minus 12 degrees, only you'd have to put in radians. Follow me? And the H field always lags the E field. That's the real thing I'm getting at. It lags by this much. It'll lag always by the phase angle. I don't know if Dave Irwin taught you this in circuits or whoever you had, but there used to be a saying, Eli the Iceman. Now, E was the symbol, and it still is in Britain, for the voltage. I is current. Well, Eli, E in an inductor, or voltage in an inductor, is always leading the current by 90 degrees. I don't know if you remember that. Right? The voltage in an inductor always is ahead of the current by 90. And then the Iceman, the current in a capacitor is always ahead of the voltage by 90 degrees. Did anybody ever hear that saying before? Eli the Iceman. You're going to hear that. You're going to hear a lot of different things, memory devices. And I can prove that if you'd like, but that's true when you're dealing with inductors and capacitors. When you're dealing with things that are propagating in a media that's lost, if there's no loss, then E and H are in phase. Remember that. There's no loss, E and H are in phase. They have identical equations except for the magnitude in front and the orientation. And you can always get the orientation because, you know, E cross H is the direction of propagation. Remember that. But this is like an inductor. The media we're in here is like an inductor. And instead of being 90 degrees out of phase, it'll be out of phase. The H field will always lag, or the current, you think of it, H is in amps per meter, E field is in volts per meter. Well, the current, or the H field, it's really current per meter, the H field will always lag by the phase angle associated with the intrinsic impedance. And the most it can lag by is 45 degrees, remember that. The most, if you have the lossiest media in the world, still, alpha will be equal to beta. And let me just show you this. Lossiest media in the world. So if you look at, first of all, what eta is, it's equal to square root of j omega mu over sigma plus j omega epsilon, right? If you have a very, very lossy media, you can assume that j omega epsilon goes away. This is super lossy. Do you agree with me? Right? Because sigma will be so much bigger than j omega epsilon, it dominates. It's as if there is no displacement current. Can you follow me on this? Well, what is the square root of j? I spend a little time talking about this because I feel it's important. Well, j can be rendered as what? It can be e to the j pi over 2, can't it? Isn't that a normal way of describing j? It's e to some angle. E is which e to the j pi over 2 is e to 90 degrees, or it's j, isn't it? Well, what's the square root of e to the j pi over 2? That's e to the j pi over 4, isn't it? Agree? Well, that's e to the 45 degrees. And if you use Euler's analysis, that's the cosine of pi over 4 plus j sine of pi over 4, or it's equal to 1 over the square root of 2 plus j over the square root of 2. Can you all see this? Right? And that's equal to 1 plus j over the square root of 2. And furthermore, I can go on and say this. Right here, I could say that this is going to be equal to square root of e to the j pi over 2, that's j, omega mu, over sigma, and that's equal to really e to the j pi over 4 times square root of omega mu over sigma, and really that's e to the j 45 degrees, or 45 degrees times square root of omega mu over sigma, and that's the largest possible angle that you can get. So this phase difference here, this will never be beyond 45 degrees with respect to the phase of the actual E field. And consequently, if you have the H field, the E field can only lead by 45 degrees. It can never lead by more than 45. Now, one last thing that's important. Since gamma is equal to alpha plus J beta, and gamma is equal to the square root of J omega mu times sigma plus J omega epsilon, in the lossy, this is very lossy media, which means sigma is much, much greater than omega epsilon. If that's the case, then here you can see when I get rid of J omega epsilon here, and I have this, then I have J or e to the J pi over 2 square root, or I have e to the J pi over 4 here, times the square root of omega mu sigma. And then again, you have 45 degrees difference. So when you have when you have gamma, you're going to have alpha equal to beta if it's very lossy. Do you follow me on this? As a matter of fact, if you put in 1 plus J over the square root of 2 here, then you get really 1 plus J, and it's going to be equal to the square root of pi f mu sigma, because omega is really 2 pi f, right? And if you divide that by the square root of 2, right, you're going to get rid of the 2, and you get pi f mu sigma, 1 plus J. And that means that this is both alpha and beta in a very lossy medium. With me? One last thing I'm going to mention about this. This quantity here, square root of pi f mu sigma, you see all the time, and it's used for the skin depth. And the skin depth is 1 over alpha and 1 over the square root of pi f mu sigma. I'm trying to hit the high points about this when you're dealing with media, lossy media. Now that is not the skin depth for this particular problem, because it doesn't have a 45 degree difference. But in general, that's how you get skin depth, and that's assuming that sigma is much greater than omega epsilon, okay? And I talked about skin depth, I think, didn't I? I haven't mentioned skin depth here. Well, you're gonna hear, I'm sorry, you're gonna hear all about it. You get into that in chapter 6, and this is EMAG 2. I wanted to put this up here because you have seen this, I know that, right? For lossy material right here. Do y'all remember this class? We did propagation in the lossy media. Do you remember? I know I taught you this much, right? No? Kind of, sort of. All right. Well, we've done general form of propagation. You remember how we got, in general, this equation right here only was sigma plus J omega epsilon? Y'all remember that? All right. Well, for this case, if it's, I'm gonna say this today, and I'm gonna come over here and do it. We went through the general equation and we said that gamma was equal to alpha plus J beta, right here. And we know that gamma is equal to the square root of J omega mu times sigma plus J omega epsilon. Now that's generally true, right? And that's equal to alpha plus J beta. With me? Now, let's go through some possible cases. Case 1 will be no loss, or a lossless environment. A lossless environment means sigma is 0, basically. There's no loss. Now, if sigma is 0, this is important. If sigma is 0, then when we look at, and let me put the equation for eta too. Eta is equal to square root of J omega mu over sigma plus J omega epsilon, or eta is equal to J omega mu over gamma, either one. But now we can take a look at something. If it's no loss, then the first thing you see is for eta, eta is equal to the square root. If it's no loss sigma 0, it's just j omega mu over j omega epsilon, or it's really the square root of mu over epsilon. That's important. There's no phase. It's just the square root of mu over epsilon. And by the way, for free space, or air, then you can see eta is just square root of mu naught over epsilon naught. This is very important. Or it's 120 pi ohms, or it's about 377 ohms. It's actually 376 point something, but I always call it 377. Y'all with me on this, class? Now that's if it's lossless, and this would be if it's free space. This is generally lossless, it's square root of mu over epsilon, and this would be free space. With me? Now, next, for this, also, if we look at the propagation constant, that's j beta, or sorry, alpha plus j beta, that's the way it's usually rendered. Alpha plus j beta. Then you can see that's square root of j omega mu times 0 times j omega epsilon, right? Because sigma is 0 right here. Agree, class? Well, what's that? That means gamma is equal to 0 plus j beta, and that's equal to j omega times the square root of mu epsilon. And therefore, beta is equal to omega times square root of mu over epsilon. With me? This is again for a lossless medium. Okay, yes?
Why was alpha equal to 0?
Well, take a look at this. Do this equation. It's j omega mu times j omega epsilon. So it's j squared. Square root of j squared is j, right? And then I have omega times omega is omega squared. Square root of that is omega, right? And then I'm left with the square root of mu epsilon, right? You can see there's no real part. It's just 0, isn't it? So if there is no real part, alpha is 0. You can't have attenuation without loss, and loss always is, it's either going to be sigma, or there's something called the lossy permittivity constant, epsilon double prime. But you don't, that comes later. Okay? Now, one other thing about this, what is phase velocity in general? It's omega over beta, isn't it? So here, omega divided by beta would be equal to 1 over the square root of mu epsilon. And that's generally phase velocity in a lossless medium. That's the general form, if it's lossless. Now, if you're in a vacuum, or if you're in free space, what happens? That's right. Then the phase velocity goes to c, 3 times 10 to the 8th meters per second. That's important to know. Okay. Now that's case 1. That's no loss. A special case of no loss is free space. And eta is 120 pi in free space. Beta is just omega times the square root of mu epsilon, or really omega over c. So in free space, you could say that beta in free space would be equal to just omega divided by c. That's for free space. Again, this is air. I'm going to specify that. Now, that's no loss, and then free space. Case 2 is going to be lossy medium. That means sigma is much greater than omega epsilon. In that case, when you look at this, gamma is equal to square root of j omega mu times just sigma. There is no omega epsilon because it's assumed sigma is so much greater than that. And that means this is going to be equal to simply 1 plus j times the square root of mu, or pi f mu sigma. Now the way I got that was I replaced j with simply 1 plus j over the square root of 2. And I replace omega with 2 pi f. And when you go here's what really happens. I did this before. I get the square root of, and this is going to be 2 pi f mu sigma. That's this. Now, the j, remember, j is rendered as 1 plus j over the square root of 2. When I go ahead and take the, I'm sorry, not j, but the square root of j. Square root of j is 1 plus j over the square root of 2. Now when I put that outside here, I have 1 plus j here divided by the square root of 2. And you can see I can take the square root of 2 inside this root symbol, and so it's 2 over 2, and therefore you will get 1 plus j times the square root of pi f mu sigma. And it also means here that alpha plus j beta is really something where alpha is beta in magnitude. So you can just go ahead and put, if you want, you could put alpha or beta outside and just put 1 plus j here. Are you with me on this, class?
How does alpha equal beta?
Right here. Look at this equation. When I take a look at this, I have 2 pi f mu sigma divided by square root of 2 pi f mu sigma. Well, that means it's going to be pi f mu sigma, right? Now, when I have 1 plus j outside, I take 1 plus j right here. Well, 1 plus j times this. This means this has to be alpha and beta because it's equal to, gamma is equal to alpha plus j beta, right? So this is, in fact, is equal to the square root of pi f mu sigma. Let me do it that way. Now that's a very lossy medium, all right? Now when it's in between, it's not very lossy. When the third case is, when you have sigma of the order of omega epsilon, so it's not real lossy, but it's not lossless, or really low loss. In that case, then you have to do the full set of equations. Then you've got to just say alpha plus j beta is equal to, and you've got to go through the root symbol, square root of j omega mu, sigma plus j omega epsilon, and you have to say that eta is equal to the square root of j omega mu over sigma plus j omega epsilon. Now you have to do that. And these are going to be complex. This is generally, they'll be complex numbers. This will have a magnitude and a phase angle. It's going to have some magnitude of eta, e to the j phase angle of the intrinsic impedance. The phase velocity in this case will be equal to omega over beta, but you have to calculate beta from this equation. So it's no longer just one, it's not a simple equation in general. I will say one other thing. For the lossy medium, I didn't mention this. Since alpha equals beta, what is the phase velocity? Well, phase velocity will always be omega over beta. With me? So that means it's omega, and that's 2 pi f, divided by beta, which is the square root of pi f mu sigma, right here. So you can see that's 2, and then it's times square root. Oh, let me do it this way. I'm going to go ahead and do it this way. I'm going to have 2 pi f squared over the square root of pi f mu sigma, because the square root of 2 pi f is simple, or 2 pi f squared is 2 pi f. And now you can see what's left when you do this. Now I'm going to have 2 squared, or 4 here. I have pi squared over pi, leaves me a pi. I have f squared over f, leaves me an f. And then I have divided by mu sigma. And that's the phase velocity. Okay? I know it seems like a lot of stuff, but really the essentials are these equations. Gamma is equal to alpha plus j beta. Eta is equal to, what do I have it over here? Yeah, eta is equal to square root of j omega mu over sigma plus j omega epsilon. And the phase velocity you always get from omega over beta. These always are true. And that's what it comes out to be. Now, I want to just mention one thing. When you're talking about something like a metal, that's sigma of the order of 10 to the 7th. For copper, it's, or 10, okay. For copper, for instance, sigma of copper is 5.8 times 10 to the 7th, and it's 1 over ohm meters. That's typically, now if you think about this, and you got an electric field that somehow penetrates in here, and it rapidly decays, but the velocity it moves at is found using this formula. Or you can calculate it this way. And just for kicks, take a look at this. Let's assume I have a wave. Let's give F equal to 10 to the 6 hertz. I want to do an example to show you how slow this is traveling compared to the speed of light. This is in a metal though. All right, if I have 10 to the 6th here, and I assume mu is just equal to mu naught, and sigma is sigma of copper. So those are my assumptions. I'm using copper and I have a megahertz waveform. How fast is the phase velocity? Well, it'll be the square root of 4 pi times 10 to the 6th over, and this is going to be 4 pi times 10 to the minus 7th, right? That's mu. Sigma is 5.8 times 10 to the 7th. Well, what do you see the phase velocity of that being? The 4 pi's cancel. I have 10 to the 6th minus 10 to the 7th is going to be, or I'm sorry, this 10 to the 7th, that 10 to the 7th cancel. So I have the square root of 10 to the 6th over 5.8. What is that?
415.
415 meters per second. Compare that to the speed of light, which is 3 times 10 to the 8th meters per second, right? That's safe. This is almost nothing. Follow me on that? And this is the unusual thing that metals, the rate that the wave travels into the metal, first it decays very rapidly. Second, it's super slow compared to the velocity in air. Now usually, I'm just going to mention this, when you have something like a conductor right here and another conductor here, and it's in the form of a transmission line, then the actual wave is carried in the dielectric. That's where the electromagnetic energy is. It's not inside the wire. The fields inside the wire just vanish. All right, class? Keep that in mind. The conductors act like they're almost guides to the wave. In fact, you could think of them as a waveguide. When you have any type of electromagnetic power flow or energy flow with conductors guiding them, all the energy is primarily, just about all the energy is outside the wires. It's never inside the metal. And that's something to keep in mind. The metal is one of these things. It acts sort of the way, if you think of, why if you throw water on a wall, does some stick or drain down, the droplets stick to the wall? Well, there's a force of attraction to that wall, right? There's something that holds it there, and the wall acts like a guide to the water. It's the same way with electromagnetic energy. The metals, this is something that's later on, and in graduate school you learn about. The metals act like something that just guides the electromagnetic energy. It doesn't really, the energy is not inside the wire, but that's important to know. There is some current flow, but it's all on the surface. All right, another problem? Since I did the spiel.
Can we do 531?
Sure. And I've always felt this, when I used to teach circuits, I'd go through the theory very quickly and I'd spend most of the class period doing problems. In electromagnetics, you have to spend a little more time developing the theory, but I'd rather do problems because that's where you expose how theory really applies. And you get a real understanding of what the mathematics is talking about. Go ahead and give that to me.
Given some
5, is it 31, did you say, or 35?
31.
Okay, go ahead.
Given at some point distance from a source at the origin in free space, the E field of RT equals 8 cosine 9 pi times
9 pi.
times 10 to the 6 T minus beta R is in the direction of theta.
8 theta,
Yes, sir. Volts.
volts per meter. Go ahead. What did I ask?
Find the frequency, phase constant, and, H field.
What else did they say? I mean, is this an air? Does he give?
Is free space?
Free space is, okay, free space. Free space is great stuff, because now you know the phase velocity is c, or it's 3 times 10 to the 8 meters per second. You know that. And you know that omega over beta is equal to the phase velocity, right? All right, so right away, looking at this, what's omega? Well, let me rearrange this. We're after beta. So from there, I can say that beta is equal to omega over the phase velocity, and I'll stop for a second. Do you all agree with that? By inspection, what is omega?
9 pi.
It's just coefficient of t inside the cosine, absolutely. So that's 9 pi times 10 to the 6th, or 10 to the 6th, pardon me, divided by, phase velocity is 3 times 10 to the 8th. So that means that's 3 pi times 10 to the minus 2, right? That's an 8, not much of an 8, but it's an 8, and that's a 6. And you could tell me what that is. That's 0.09 something, isn't it? I don't know exactly. What is it? Ivan, do you know? 0.0942. All right, so that's radians per meter. What else do they want?
Frequency.
Okay, how do we get the frequency?
Omega over 2 pi.
That's right. We know that 2 pi f is equal to omega, so f is just omega over 2 pi. And by looking at this, if I divide this by 2 pi, I get 4.5 times 10 to the 6th, right? So that's equal to 4.5 times 10 to the 6th hertz. What else?
H field.
All right, now we're in free space, right? We know eta in free space is equal to what? In general, eta is equal to j omega mu over sigma plus j omega epsilon, correct? That's the general equation. Please get used to writing that several times, it'll stick with you. Now, what about free space? What's the value of sigma in free space, or in air? It's 0, right? So that reduces this equation to just the square root of mu over epsilon, right? But there's one more caveat. In free space, what is mu, what is epsilon? Mu naught, epsilon naught. So mu naught, epsilon naught, and that's equal to 120 pi ohms, right? And now I know the ratio of E in free space, magnitude, over H in free space is eta. So therefore, if that's the E field, the H field will be equal to, in magnitude, will just be the E field, 8, divided by 120 pi. And can you give that to me? That's the magnitude of the H field.
0.20944.
0. Go ahead, say it.
20944.
Is that right? 8. 0.002 something. All right, that sounds right. Now that would be the magnitude of the H field. Does he have that?
I think I'm missing part of it.
Anybody, can you tell me? This has to be the right answer. I mean, this is the right answer, but I don't know what is in this book, I guess. Gaines, can you find that? 231?
He has H of R and T equal to 21 cosine
21 what? What units?
milliamps.
That's what we got. We got 21. So this is about 21 milliamps. 21 milliamps per meter. It's per meter. And it would have the same cosine argument, multiplying cosine of 9 pi times 10 to the 6t minus beta r. And here, of course, beta we calculated right here so you could stick that in the equation. One other thing though, I'm gonna tell you this, the direction of propagation has always gotten that E cross H is really the direction of power flow, and a unit vector in the direction of the E field crossed with a unit vector in the direction of the H field is a unit vector in the direction of propagation. And that's how I always tell people we get it. E crossed H is the direction of propagation. Now, if we wanted to know the direction of the H field, we know E is A theta, right? Please watch this. That means a direction of the E field unit vector is equal to A theta. Now, what's the direction of propagation, unit vector in the direction of propagation? Well, where do you always look? You look at the coefficient of beta, right? But for beta, the minus sign tells me it's traveling in the positive direction associated with its coefficient. So it's traveling in the R direction. Do you all see this, class? That means the unit vector in the direction of propagation is AR, right? Now if you come here, I know unit vector in the direction of propagation, or in the direction of the E field, which is A theta, right? Crossed in a unit vector in the direction of the H field is equal to a unit vector in the direction of propagation, which is AR. And I do this, I know it's R, comma, I should draw this. When you're thinking about vector senses, this is the origin, and you have a vector. AR would be radially outward, A phi is in that direction, and A theta is coming down. Now, if you take a look at this, if I have A theta crossed into AR, it's A phi crossed into AR. Boy, it's a hard thing to show. Crossed into AR. If I cross theta here into R, right? Theta cross R, it would be coming up this way, be minus phi crossed into R be minus A theta. So for this one, we have, what would give us, what do I cross A theta into to get AR? So pardon me? It would be minus, well, no, minus A phi. AH is going to be minus A phi, right? I'm trying to draw this thing so you get a three-dimensional perspective, because its cross products are easy if you see this. Like, if you think of Cartesian coordinates, if you have X, Y, and Z, I can see X cross Y is Z, Y cross Z is X, and then Z cross X is Y. That's easy to see. This perspective, it's a little tougher because I'm trying to show you AR in the plane of this board, A phi coming perpendicularly outward, and A theta going downward, all right? Now, if you look at this, if I have A theta right there, that's going down. Crossed into something gives me AR. Well, it has to be equal to minus, it has to cross into the board, minus A phi. Can you follow me on this, class? That's where the minus A phi sense comes from. So the H field, if you want to be completely accurate about it, you could say it's minus, and whatever the value of that is, 21 milliamps here, times cosine of 9 pi times 10 to the 6th t, minus whatever beta is, R, and it would be in the A phi direction. Are you with me? Because I took the minus sign right there. Does he have that? Now, if you want to get rid of that minus sign, you can add or subtract 180 degrees inside this cosine argument.
Yeah, he doesn't have it. Minus.
Does he have 180 degrees in here?
No.
Does he? Let's start him off. Let me see that phone. No, I want to see the phone. I'm going to see one other thing. In his appendix, I don't know if he has the unit vectors in the appendix are not. I posted these and it was a chapter 3, he does the unit vectors, I think.
I know the pictures.
Yeah, what I'm trying to do is get a better picture of that. Is it chapter 3? I think so. Thank you.
That's not the expensive.
Yeah, but he doesn't show the unit vectors real well. Does he do this for spherical? No. I posted this unit vector stuff, if you remember. Do you remember that? I try to give you the best visual on this, because if you can see this in your mind, then it's easy to understand E cross H is direction of propagation. And remember, use the right hand rule. Index finger on your right hand in the direction of the first vector you're crossing into. You just use that and rotate in the shortest angle using your thumb as like the pivot point into this vector. It results in that vector. Your thumb points in that direction. And let's see. You know, for Cartesians, the coordinates are X, Y, Z, right? Then it's rho, phi, Z for cylindrical, and then it's R, right? R and theta, phi, R, phi, theta for spherical. Do you remember this? Wait a second. R, you know, you're right, and by the way,
That would make it.
that, I got this wrong. That's A phi. That would make it positive, you're right. That's my bad. You're right, phi goes that way. And I just want to tell you one other thing too. And this is the problem I have. When I teach radar, we use really the aircraft or the aeronautical industry's symbolism. So instead of R, theta, phi, right, the way we get it, now we're going to get R, phi, and they call it, they call it, it's the actual, the radial distance, then it's elevation, and then, elevation and azimuth. They use this symbol. They do it backwards, is what I'm trying to tell you, that in the aircraft industry, you're used to seeing theta being here, you're used to seeing phi being a measurement here, and this being R. That's the way it is in spherical coordinates when this is X, Y, and Z. Well, in the aircraft industry, if they're talking about a radial distance, this is still R. And then the elevation is this. That becomes the phi term though, and this dimension is measured from here, and it becomes theta. It's from the axis of the bore sight. So I'm going to tell you, when you get into different, most of the time in electrical engineering, we always use this symbol, theta there, R there, and phi there. In electrical engineering, in communications, in antenna theory. But in radar, we use the aeronautical symbolism, which always drives me nuts, because now they use elevation and azimuth, and elevation has to do with what the angle is with respect to the ground, not with respect to the vertical, right? The z-axis. And azimuth always has to do with what's called the bore sight, or especially for radars, it's where the radar is pointed and the angle off the bore sight that it makes, the R makes with respect to the bore sight of the radar, or where it's shooting. And that's one of the things that you're going to have to get used to, different ways of designating angles. And I'm warning you about this because when I was at NASA, I remember this is the first time I ran into this stuff when I was doing summer fellowship at NASA. And MATLAB, by the way, is set up so when you look at, if you wanted to go from, they have functions that do this, you go from Cartesian coordinates to spherical. They give it in terms of the aircraft industry or the aeronautical industry. They give it in terms of R and then elevation and then azimuth. So I'm gonna warn you, when you go cart to spherical in MATLAB, you don't get spherical coordinates that are associated with the theta and phi that we're using here. Just remember these things, because you're gonna find out that you're gonna save yourself a lot of anguish by not assuming theta is the same measurement for all, I guess, papers and discussions that you see. Any other questions? Anybody? We got 5 minutes roughly.
How long is the test gonna be?
Well, there's probably gonna be 5 questions, and each one will have multiple answers, 5 pages. I mean, but I haven't made it out if it's where you're going. So I'm assuming it's five pages, and it'll be, if you know my tests, you look at my old tests, you can look at the homeworks. That's basically where the material comes from. And that's the way I make out a test. I go through and take a look at the homework, the things we covered in class, and then I'll take something and I'll modify it so the concepts are brought out, but it's not, sometimes they are identical. I've done that more than a few times just to see if people know what they're doing on the homework or have done it. But they are not, you haven't had Dr. Riggs, but you're gonna see if you have Dr. Riggs. His tests are, he'll come up with a problem where you're gonna have to solve a del squared E or del squared V equation and find the actual differential solution to find the capacitance of something. And those are, I don't think anybody ever gets them right, but he wants to see how you think. I don't do that. And I don't know how Dr. Gross is, but some of you have had Dr. Gross. Not good, huh? Is he somebody that asks things?
He asks random tidbits of facts.
Random tidbits. I mean, you had my first test. I thought it was fair. I think you saw it was based on the homework, didn't you? That's the second one. By the way, these two guys, Ryan, Andrew, Ryan Olson, Regan.
Yeah. I can get Andrew.
And Ryan?
I'll sit in just a minute if you want me to take it.
Now, let's see. It's gonna cover, the test covers everything from the last test where we left off. So, on the last test, you didn't have inductance, did you? No, you had a capacitance problem. All right, so you're gonna, and did you have a resistance problem too? Yeah, you did. All right, so you're gonna get inductance, induced EMF, plane wave propagation. I guess you're gonna get, if you take a look at the homeworks from the last test, that's basically where I'm gonna draw from. But you have to know the previous material too. That's the thing about this. You've got to know, how to, the different coordinate systems, how to work with the really all the coordinate systems. You have to know what the E field is, the H field, and so forth. But remember that induced EMF problem. Remember, those are the ones that are a little more tricky at times. Okay. I don't know what else I can tell you. This was meant to be a review. And that first part that I went through was probably, it really underscored the relationship of gamma to alpha and beta, to phase velocity, and to intrinsic impedance. And those are things you have to know too. Any other questions? If you have any questions, shoot me an email. If you need to see me tomorrow or later today, let me know. I teach from 1:15 to 2:30 today. I'm in 238. When I'm done with them, if you need to see me, just hang out there and I'll go to my office. All right. Any other questions? One last thing I tell people, if at all possible, get your sleep. Sleep does more good on a day of a test than really anything. And I can honestly tell you this, that in my life, I have seen 8 o'clock classes, especially on Friday, have horrendously low averages. And it's because they stayed up studying, and they burn themselves out, and then they make all sorts of stupid mistakes and can't recall things. The best test scores are usually 10 o'clock and later tests on a Monday, almost always, because they get their sleep and they have the weekend to study. That's just my observation. Now, please get your sleep. And if you wanna bring a coffee in here or Coke or something like that, or something, you can, but nothing that makes noise like potato chips. I'm just asking you to do that. And don't bring Chick-fil-A into this, Dr. Gross says,